equations. We're talking about equations where x is raised to powers like 17, maybe more, with this like endless string of coefficients. Traditionally, that's just been a massive roadblock in algebra. But this deep dive is all about a groundbreaking new method, one that promises to fundamentally redefine how we approach these kinds of mathematical puzzles. Ezouidi's theorem.
Yeah, and what's really striking here, it's truly fascinating, is how Ezouidi's theorem directly confronts what we've long seen as a fundamental limit in math.
Yeah.
It's not just about finding another technique, it's about potentially shifting our whole understanding of what's even solvable in an exact sense, especially when you're dealing with polynomials of such high degrees. It really challenges the very boundaries we thought existed.
Okay, so maybe step back for a second. Why are these high degree polynomials such a headache? Like, picture an equation stretching across the page, x to the power of 17 plus all these other bits. For decades, right, when you face something like that, you typically turn to numerical approximations. You might have heard of methods like Newton's method.
Sure, yeah.
And while they're incredibly useful, these techniques essentially work by making better and better guesses, trying to get close to the answer. They're powerful, absolutely, but they inherently carry a margin of error. You run the risk of rounding errors, and you certainly can't guarantee a perfectly precise exact value.
Right. And this brings us neatly to Abel's theorem, which is really a cornerstone of classical algebra. For a long time, Abel's theorem asserted that certain polynomials, specifically degree 5 or higher, just cannot be solved using radicals, which, basically means you can't find their roots using a finite sequence of simple operations, things like addition, subtraction, multiplication, division, and basic root extractions like square roots or cube roots. Ah, okay. So that theorem effectively set a boundary.
Exactly. It dictated what mathematicians considered solvable in that exact symbolic sense for, well, a very long time. It was a known limitation.
Right. Here's where it gets really captivating, though. Ezouidi's theorem, developed by Mourad Sultan Ezouidi, steps in with this revolutionary approach. It directly contradicts these classical limitations, including that long standing assertion from Abel's theorem. It's not just an alternative to approximations, you see. This method demonstrates that even polynomials previously thought to be beyond exact solution can be solved precisely. It doesn't give you just a close guess, it provides exact symbolic solutions, revealing precise, unambiguous roots for polynomials that were, well, pretty much deemed unsolvable by conventional means. Okay, to really get our heads around this, let's look at a specific example. A really daunting polynomial equation that Ezouidi's theorem tackles in the source material we looked at. This isn't some simple quadratic or cubic, folks. We are talking about a polynomial of degree 17.
17. Yeah.
Yeah.
Just to give you a sense of the scale, imagine an equation that like nearly fills an entire page, starting with Alice by 17, then 16 more terms, each with its own specific very complex looking. And the goal here, solve this exact high degree polynomial precisely. No approximations.
So how does it do it? How does Ezouidi's theorem deliver these exact solutions for something so complicated?
Well, it employs a really systematic recursive process. First, the polynomial is expressed in a general form. It uses what we call symbolic coefficients. Think of them as placeholders. It spotlights values like 0 by 16 plus 1 by 15 is 0 by 14 plus, and so on down the line.
Oh, okay. Symbolic placeholders, edits values. Got it.
Now, the core brilliance of the theorem, it lies in a specific formula. This formula computes these carry coefficients recursively, step by step, like a chain reaction where each calculation builds exactly on the results of the one before it. This ensures no approximation ever creeps in. That's crucial.
This formula involves things like binomial coefficients, those numbers from Pascal's triangle, and terms that progressively adjust the degree. It's intricate. But this recursive calculation is absolutely vital because it ensures we're always working with exact symbolic values, not numbers that have been rounded.
That sounds incredibly precise. So, what happens when you apply this method to that monster degree 17 polynomial we mentioned? Do those values end up being just as complicated as the original equation?
Well, that's where it gets truly remarkable. Honestly, it's quite surprising. When these coefficients are calculated using the theorem for this specific polynomial, you find a surprising sparsity. A lot of them just turn out to be zero.
Really? Zero?
Yeah, quite a few. In fact, for this particular polynomial, the first 7 coefficients for us, all the way through 6 star, they're all zero. Then 6 turns out to be a very specific exact value, minus 200 to 309 times 17 to the power of 8, an exact number.
Wow.
And after that, 6r through S14r, all 0 again. And then S15r is revealed as another precise value, 5324028 times 17 to the power of 16. And finally, S16r is also 0.
That's incredible. So all that complexity kind of collapses. Does this sparsity tell us something deeper? Is it just a feature of this specific polynomial, or is it something the theorem reveals more generally?
That's a great question. It's a bit of both, I think, and that's a crucial insight. This isn't just about making it simpler to calculate, though it certainly does that. It suggests that for certain seemingly complex polynomials, there is an inherent, almost elegant simplicity hiding underneath, a structure that traditional methods might just obscure. The theorem's recursive nature beautifully exposes this underlying structure. It's almost as if the perceived complexity is just a kind of veil. And Ezouidi's method uniquely lifts that veil.
Okay, so how does that simplification play out?
Well, this incredible sparsity then dramatically simplifies the original polynomial. All those zero coefficients basically make their terms vanish from the equation. So that initially immense polynomial reduces right down to px, x times by 16 plus s7r by 8 plus s15r, much cleaner, much cleaner. And this further simplifies into two core parts. Either the first factor, x is 0. So x is 0 is one of our exact roots right there. Or the second part is 0. But by 16 plus S7R by 8 plus S15R equals 0. And we can then substitute those exact S7R and 15R values we just found, which gives us a much, much more manageable equation. By 16R, 24309 by 178 by 8 plus 5324028 by 1716 equals 0.
Okay, still looks a bit intense with those big numbers, but it's way simpler than the original 17 terms.
Exactly. And from the significantly simplified form, the exact symbolic roots can then be derived. What's fascinating too is that these exact roots are often expressed in terms of complex exponentials, which is a very precise mathematical language. It's used to describe numbers that combine real and imaginary parts, like going from a blurry photograph, maybe from those numerical methods, to a perfectly sharp, high definition image. You get the precise mathematical blueprint of the root, not just a numerical readout close to it.
So, boiling it down, what does this all mean for us? The core strength here, the real takeaway, is that Ezouidi's theorem doesn't rely on numerical approximations at all. That feels like a monumental step.
It is.
It means the roots it derives are exact, completely free from those potential errors, those uncertainties you get with traditional methods. This approach ensures this unprecedented level of precision, even for polynomials that we previously thought were just way too complex for any classical method to give exact symbolic solutions. But thinking practically, what about the effort involved? Or are there limits? Situations where maybe numerical approximations are still, the better tool for the job?
That's a really good point. It's important to be realistic. While Ezouidi's theorem offers these exact solutions, the computational complexity, for really high degree polynomials without that kind of elegant sparsity we saw, well, it can still be substantial, but crucially, it delivers a level of precision that numerical methods just cannot achieve. So if you need a quick estimate, and maybe extreme precision isn't the absolute top priority, or maybe the exact symbolic forms are just too unwieldy to work with easily, then yeah, numerical methods certainly still have their place. They're valuable tools.
Okay.
But if you need to know the exact root, maybe for fundamental scientific research, complex engineering design, or just pure mathematical exploration, then this method is, well, it's a game changer. It really reinforces the idea that knowledge is most valuable when it's not just understood abstractly, but when it can actually be applied to solve real problems. And it definitely encourages critical thinking because we're witnessing a seemingly impossible problem being solved with exact precision. It forces us really to question those long held assumptions.
So, to sum up, Ezouidi's theorem genuinely reshapes our understanding of what's possible in algebra. In solving these really complex polynomial problems, it's a significant breakthrough.
It really is. And this raises, I think, an important question for you, our listener, to ponder. If a mathematical theorem can overturn centuries old assumptions about what's possible, what other challenges out there, things we currently label as unsolvable, might simply be waiting, waiting for a new perspective, perhaps, or just a different approach
Yeah.
to unlock their exact solutions?
Something definitely worth thinking about. Thank you for joining us on this deep dive.